Section 223, Applications of Gauss's Law. So we're going to take a break here and really see what Gauss's Law does for us. You know, people that have been exposed to Gauss's Law forget that you can actually solve electric field problems using the integrals through the traditional approach of, of how we solved the problems earlier. And there's good reason for that. Gauss's Law really makes things super duper easy. So example 2 is basically it's the same, I think, as problem 2.7, I believe. Let me go back and double check. Yes, it's the same as problem 2.7, which is a hard problem, but we're going to solve it here with just hand waving and smiles, thanks to Gauss's law. So we have a surface, a spherical surface of radius r. Let me draw what that might look like. So we have a circle, which is a sphere, and it has radius r. And oh, I'm sorry. They want us to find. I've already screwed up. Can you believe it? Let's draw this again. Okay, so we have a sphere, radius a. Okay, and they want to find the electric field outside of this surface. So we pick a Gaussian surface. It doesn't matter how big it is, just as long as it's a sphere that's centered on that sphere, and it has some radius. We'll say r. And Gauss's law states rather unequivocally that the flux of that surface, E dot dA, is going to equal 1 over epsilon naught, the total charge enclosed. What does that mean in this case? Well, the total charge enclosed is just the surface, is just the total charge of that sphere, Q. And thanks to symmetry, thanks to the fact that we know that the electric field has to be pointing in the same direction at every point along that sphere, just because there's really no way to orient it, we can say that this integral, the surface integral, is the same as the integral of E vector dot dA vector is the same as the integral of the magnitude of E times the magnitude of that area. So we can just drop the vector notation right away. So what do we get out of this? Well, the E is going to be constant, so we can pull that out of the equation. Let me pull the right marker here. That's equal to E, which is constant, integral dA. Well, what's the surface area of a sphere of radius r? It's just E times 4 pi r squared. So the electric field at any point along this Gaussian surface is going to be equal to the charge enclosed. E is equal to 1 over 4 pi epsilon naught Q over r squared. So these two come from Gauss's law, the Q and the epsilon naught, and the 4 pi r squared comes from the surface area of that Gaussian surface that we've used. Which direction does it point? Well, obviously it points outside, given that it has a positive charge on the inside, so it's, there you go. We've solved the electric field for a sphere with surface charge of total Q. And we're done. And you might have seen that it took me 15 minutes to work through that problem, that equation. I'm kind of stumbling and fumbling the way through, but here we have a solid answer. And the hardest part was finding the surface area of a sphere.